Okay, so last time we were working with the calculus of vector-valued functions, and we had done some things with derivatives.
Is it still section 12.2?
It's still 12.2, yeah, we're working in. And we had gone through what we called example 5. And what we're going to take a look at next is the inverse, if you will, of derivatives, which is antiderivatives, the opposite, right? And we're going to do a couple of definitions first before we start with that. All right, so the first definition says what an antiderivative is in this realm. The vector valued function, capital R of t, is an antiderivative of the vector valued function and it's small r of t whenever capital R prime of t is equal to the small r of t. There's something about this definition I want to make sort of clear in case you didn't pick up on it or don't remember the details. It doesn't say that capital R of t is the antiderivative. It says it's an antiderivative. Do you guys remember why that would be? What's the deal with that? You got that plus c business going on, right? So there's multiple antiderivative options. This is just going to be one of those options. What is it that you need in order to actually find the antiderivative of something? What's that? Okay, well, we're going to do an antiderivative, we're going to do an integral, but how do we find the antiderivative as opposed to any antiderivative? There's one other piece of information we have to have. Not that, but you're really close. We don't need a beginning and end point. You're thinking about finding a definite integral, I think. We have to have some point. Any point on the curve. Sometimes it's called an initial condition. It doesn't have to be a first point because there's no such thing as a first point. But you have to actually have a point on the curve so that you can eliminate this ability to sort of shift things up and down with the plus c at the end. That's what has to happen. So sometimes we have that given to us and sometimes we don't. So sometimes we can find the plus c value at the end and sometimes we can't. All right, one more definition. Actually, two more. I lied. I know I shouldn't lie. All right, definition 2.5. If capital R of t is any antiderivative of R of t, then the indefinite integral of R of t is the integral of small r of t dt, which is the capital R of t plus c where c is an arbitrary constant vector. That's what you were getting at, Ben, right? This idea of having this integral. We still don't have a definite integral here, so there's no limits on top and the bottom. That part's not there still because we're working with an indefinite integral here. I underline that. Then we have one more definition before we're going to do an example. Definition 2.6 says the following. For the vector valued function R of t, which is f of t, g of t, h of t, we define the definite integral this is the other component that you guys were getting at just a moment ago, the definite integral of R of t on the interval AB by integral from a to b of R of t dt, which is the integral of each of the individual functions. So the integral of f of t from a to b dt, the integral from a to b of g of t dt, and the integral from a to b of h of t dt. So this has the same feel to it as when we did derivatives. We're just doing it component-wise, right? We're doing the different integrals component-wise. Remember that what you're doing here when you evaluate this is you're evaluating the antiderivative of, say for instance, we're working with this one right here. You're going to find capital G of t, and then you're going to evaluate it at b and evaluate it in a and subtract those two values. Okay? All right, so we're going to do an example. Two examples, actually. The first one is we're going to evaluate the given integral. And our integral that we're evaluating is the vector function t cosine of 3t, t sine of t squared, and e to the 2t dt. And yeah, I definitely chose something interesting for us to do to help you remember some of those antiderivative rules that you guys haven't worked with in a while. Okay, because this, except for the third part, the k component, this is an interesting one. The k component's not interesting at all, but the first two components are interesting. The most interesting one's the first one. Do you have any idea how we do that? Do you remember what happens when we have t cosine of 3t and we're having to integrate that? This is the most complicated part of this particular. U substitution is an option, but it won't work on this one. It will work on the middle one. We will use U substitution on the t sine t squared. Something else. You guys remember integration by parts? Yeah, integration by parts. And I don't know exactly when Dr. Nichols worked with that with you, how he set things up. So this might look a little bit different in terms of just the ordering. But the way that I set up my my integration by parts is to set it up like this. So I've got, does he put it in that order and everything too? Great. Some people do it differently. So the way that you fill in the integration by parts is you fill in along the top to bottom diagonal from top left to bottom right. So you fill in u and you fill in dv. And you fill it in with the components of your function. So you have these two components that are multiplied. One component is going to go inside of u, and the other component is going to go inside of dv. So you might have to remember how you make those decisions. Well, as a general rule of thumb, u is something that you want to use that gets simpler when you take its derivative. For example, if I put u as t, the derivative of t becomes 1. It got easier to work with. But if I put the u in as cosine, cosine's derivative is sine, or some variation of that, it didn't get any easier to work with. It's equally difficult. So that's one of the ways that you can make that decision, and that's helpful in many cases. So we're going to let u be t, and then du would be 1 dt. And then v is the cosine 3t part with the dt. Now we need to have then the antiderivative of cosine of 3t in order to find out what v is. So what is the antiderivative of a cosine function? It is a sine function with the same angle, but the angle itself is a u substitution component. It's not a very interesting one, of course, but what would we have to do to compensate for that? We need a 1/3 in front of our sine 3t. Everybody good with that so far? All right, now we've got to put those components together in order to get the antiderivative all of this first component. So we put things in along the u and the dv diagonal, and then the solution to that integral is uv minus the integral of v du. Okay? So we go across the top, u times v, and then we have the integral across the other diagonal. Do you guys remember this now? I know it's been a little bit, but it's called coming back to you, isn't it? I'll leave that for there. Okay, so we have 1/3. Our first component is 1/3 t sine 3t minus the integral of 1/3 sine of 3t. And this is still just the first component. We haven't done anything with the second component or so forth. I'm going to actually just keep working our way down, and then we'll go to the second component next. Let's actually finish the one that we're working on before we start messing with another function. So obviously the 1/3 t sine 3t doesn't have any integration with it. It's done. What's the integral of sine? Right, and I've already got a negative in the problem between these, so I'm going to change this to a positive. So I'm going to have a cosine of 3t. But just like last time, I'm going to need another coefficient multiplier here, and so I'm going to get a coefficient on this one of 1/9. Sorry, I totally thought you said 1/2, and I knew that wasn't right. So, okay, good. Yeah, 1/9. So we have the 1/3 that's already here, plus another 1/3 because of the 3 inside. So we get 1/9. Yes, plus c. Thank you. And actually what we're going to do, well, let me do it here. We're going to have 3 C's. So we're going to label them as C1, C2, C3. So I'm just going to call the first one C1, and then I'll show you another option of how to write that when we're all said and done on this one that you could do a little bit differently too. But we'll put plus C1 for now. All right, let's go back up to the second component up here, right here. This one, like we said, we can actually do with u substitution. What would you like to let u be? T squared sounds good. Then what would du be? 2t. And we have the t, we don't have the 2. So somewhere along the way, someone might have done something like this. They might not have too. It just depends. We're going to end up with a du over 2, or 1/2 du, to replace the t dt. So in essence now what I have is I have the integral of a 1/2, I'll put it in front, of sine of u du. Is that okay for everybody? Okay, what's the integral of sine of u? Negative cosine, so we've got negative 1/2 cosine. And I'm going to go ahead and put the u value back in, which was t squared. And then I need a plus c2. Okay, the last component's the simplest one. What's the antiderivative of e to the 2t? 1/2. Say again louder for me, Jordan. Right, e to the 2t. And then we're going to have here a plus c3. So I've got 1/2 e to the 2t plus c3 down here. This works great. You can leave it written like this just fine. There's another thing you could do, either instead of this one or after this, either way, is that instead of having the C1, the C2, and the C3 written, we could put plus C outside of the vector notation as its own vector. So we could write this like this. We could have 1/3 t sine 3t plus 1/9 cosine of 3t. and then negative 1/2 cosine of t squared, and 1/2 e to the 2t, and then plus c, and c here is actually a vector c. You can either put the vector on top or not. I'm just going to put it there to remind you that it is the vector c1, c2, c3. That's why it's actually showing up outside there a little bit differently. So either of those would be a version of an acceptable answer. Okay, any question on that? You'll probably come across other features as you're working with these that you may need to remember how to do the integration for. So we'll send you to Hannah at the Success Center because they do integration all the time over there, don't you? Yeah. So this is definitely something in terms of just the integration. I know that typically Calc 3 they don't want to see you guys over there, but with integration stuff that certainly would be acceptable. So I don't think Hannah wants you to talk to her, but but certainly you can go and take a look at some of those, or come see me. That's fine too. All right, one more example we're going to do. Oh, all right, let's try this again. All right, number 7. We're going to do the integral from 0 to 1 of t squared minus 1 3t dt. Okay, so obviously this one's cleaner than the other one. I don't have any use substitutions or integration by parts. It's very nice and very clean, but we do have the integral as a definite integral now, so it's going from 0 to 1. So we have that component at the end. So let's actually start this by finding the general antiderivative. We don't need the plus c though, right? I mean, we actually really don't because we're going to be evaluating this at 0 and 1. So what is the antiderivative of t squared? All right, so 1/3 t cubed, or t cubed over 3. Good. And then the antiderivative of the minus 1?
T.
Yes, t. And then the antiderivative of 3t? 3/2 t squared. All right. And we're going to evaluate this at 1 and 0. And beautiful things happen at 0. What beautiful things? It goes away. So it doesn't actually end up having a component at 0. So what we really are going to do is we're really going to do capital R is what this functions have been using to be defined as capital R of 1, oops, minus capital R of 0. But this is 0 in our function. So we're really only going to evaluate this at 1. All right, so if we evaluate at 1, I've got 1/3 minus 1, and I've got 3/2 times 1. So what's 1/3 minus 1? Negative 2/3, and then 3/2. Now if you weren't dealing with 0 to 1, we would have to find the 0 component as well, and then subtract that component-wise from the one that we just got. Any questions on that one? Same thing. You're just going to do it 3 components. There's not any difference. Yep. That's okay. Any other questions? Okay, did everybody get the homework written down last time? Yeah? Make sure you have it. It's all good? Okay. You bet. Oops. It's okay. Okay, everybody good? All right.